obviously it will be the cost, he will misbalance it.
Yeah.
So because latency is a constraint, so he cannot violate it anyhow.
When you, the latency you have, that's only depending on the distance to the between the data centers.
Not really actually. So this is inside. I put one topology, right? So this is in.
Okay, yeah, but it's not a matter of how much resources you put in.
The latency.
Yeah.
So latency is like how much traffic you put, it will become more congested. That is the queuing latency I was mentioning. So if you put more traffic over one path, you try to, suppose you have 1 gig link,
Yeah.
and then if you put more and more bandwidth for different customers over that path, then there is a possibility will, I mean, it will be more congested, latency will go up.
Yeah. Okay. Yeah. So it's both a load balance problem and or a load problem and a distance problem.
Obviously, yeah.
Yeah. But so then it becomes a very dynamic problem. Thanks to that, otherwise it will be a more static problem.
But it's a dynamic problem, so yeah.
Which makes it much harder, and latency is normally hard. But you talk about average latency all the time, right?
Yes, average latency all the time, because
Oh.
I have 3 different VN classes, which I divided according to the classes which has different requirements in terms of resource and also the latency, and I have one class has 1000 requests, so it's come dynamically, which I showed in the figure, like it comes and different duration it follows. So then for that VN customer classes, as they previously mentioned, okay, I have a 5 millisecond bound. So when I said average latency, it's over the all request. I mean, all requests for that VN class, how much they face.
And I guess if you want to do this on smaller classes, or to do it for individual application, you would just do the same, but
Then you have multiple more classes.
yeah, but
Yes.
then you can do this the same approach for each class instead.
Yes.
Yeah, but could you instead add this tail latency for this? Which is something that gets a lot of attention these days.
Yes, tail latency is important, but I didn't consider latency between these 2 data centers, right? So I found that, and I also didn't consider the latency between the controller and the different data centers. So I only talk about inside the data center latency. So I said that you want this latency, you want to have a reservation on the path, and then how can I provide the path that I ensure that if I allocate that path to you, and if you use that path, the latency will not go that your requirement.
So, but could you then do that just as well for tail latency as for, so if I would ask for tail latency instead of average latency, would you be able to do that relatively straightforwardly, or will that be
No,
difficult?
that needs some modification, right? When you say the tail latency, I don't know exactly what do you mean by the tail latency, like
for example, the latency for the
90 percentile,
yeah,
then it should not
exactly.
be a hard constraint. It should be, I mean, it should be modeled in a different way.
So
I could not think right now how can I model it. I mean, obviously, I mean, now I put hard constraints, so that my every latency cannot be violated that. But if I say, okay, mine 90% or like, I mean, then yeah, obviously I need to remodel it in a different way. But right now I cannot, I mean, I cannot think, I mean, how can I?
Okay. So let's look at paper 6.
Paper 6, okay.
Where I would like to push you a little bit on the problem here. So I think, and I guess I'm right that your main objective is to maximize energy consumption while hurting performance as little as possible. And yeah, I realize we have already talked about some of it. So one of the 2 arguments for consolidation is that you have the resource type variations, and you have the time variations. And here,
A time variation? No, here there is no time variation.
no, exactly.
Here. Okay.
These are the 2 you have, but you have only considered the
resource
type.
variation, yeah, resource type.
Yeah. And to me, intuitive approach will be that you, for if you have just if you only have different resource types, then you could handle that by just multidimensional bin packing. If you know how much CPU you need, how much compute you need, etc., for each of them, and to optimize that bin packing. And to me, it's only when you have the time variations, where you don't know how much resources you need over time, that you really benefit from the overbooking.
Okay.
And yeah, so I would give that as a statement and have you to
Okay.
argue against me.
Okay. So what is the motivation behind this paper? So this paper, so this is VM consolidation model. So the main idea is that I want to optimize the energy, right? And the number of migration is also one of the important thing. So one thing I found, I mean, it's not the resource requirement, it's the resource sensitivity that we have mentioned in the paper. So the sensitivity means maybe you ask for more CPU. That doesn't necessarily mean that if you somehow starve for that CPU, you will lose your performance like hell. So the thing is that here main argumentation is the sensitivity. I mean, how much sensitive you are to that resource, not like how much you are asking for that resource. So then we are saying that, okay, if you don't consider this sensitivity, maybe you have the same energy consumption, because if you look at the graphs, all graphs is saying that I have the same energy bound. Here I didn't try to minimize the energy consumption. So what I tried to do instead, I said that I have the same energy bound, and this is your upper bound. You cannot go more than this energy, but you need to give that performance with the same. So your operational cost is fixed now. It's a hard constraint. You cannot violate that. So now you are trying to pack them in certain way, so then you don't lose the performance. So why I mix them? Like some is like very sensitive to the CPU. So if you somehow, because the overbooking I mentioned, because overbooking can give you the possibility of contention, and overbooking can be temporary. So you certainly jumped over, and then you have a possible overbooking, right? Then you cannot always migrate. Okay, I migrate the VM, I migrate the VM, I migrate the VM. That could be one option, but you cannot always do. Then your system is already stressed. So my main idea was there. So if I know the sensitivity VMs, how can I properly share the resources here, or how can I pack them so that I cannot, if although they starve for the request, somehow there is a temporary overbooking, so they don't hurt too much. I mean, if you can say that for the same energy bound, there is a two different level of performance throughput I put in the graph.
Yeah.
So here not the resource requirement, resource sensitivity is the main point.
It seems like your approach is based very much on the fact that you might ask for more than would really, you ask for more resources than you would actually need to get roughly the same performance sometimes, and this is what the overbooking would help. You said if you have something where sensitivity is low, that means that you could start with a bit less resources and still be doing pretty fine.
Yeah, yeah.
And this is sort of what you make use of for your
Yes,
overbooking.
right.
So a very sensitive thing here is how you actually determine what amount of resources you need. What is the baseline?
So here the baseline is like we profiled it. We
Yeah.
try to run it in a, because the motivation figure, if you look at this figure number, whatever. I have a slide, maybe I show you something.
And it's how you determine this ODK.
Yeah, so here, so there is like this figure. So here we have like, so we have two virtual machines we are running. So in one virtual machine we try to run these different applications, and here another virtual machine we are running like a unzip large files. That is another application. So we want to see that if we run this virtual machine standalone without anything sharing, and then how much performance it gets. So that means obviously it get one is the maximum throughput you can get, and because of co-location with this, how much performance you lose.
Yeah.
So we try to find out that, suppose you can see that this AIO stress is giving only 40%, but on the other hand Apache is giving almost like more than 90%. So we said that okay, Apache and these two VM can be co-located together because they don't interfere with each other, they are not sensitive. So we try to first put them on a contention and find that. That is another paper where it reveals its sensitivity values. So we know that sensitivity values, and based on the sensitive values, how can we pack them so that we don't increase the energy consumption, but still we have the performance.
I guess my question is if this really is a sensitivity throughout the whole spectrum, or if it's only the baseline.
It's only the baseline.
Yeah, well, I mean, the problem, are you really overbooking, or are you rather identifying what is the real requirements and resources you will need? So if you have something which is very unsensitive, it could be that you could do with a little CPU, and if you then ask for a little bit more, then of course it will look like very insensitive to the CPU.
So we look, also there is one figure, so where we try to find that, suppose this AIO stress, maybe he asks for 3 resources, maybe he need CPU, memory and disk. So we are saying that if you don't overbook on the CPU level, he will not, he will not lose his performance. But if you do in the memory level, maybe he will lose more. So we try to find that balance. Some is sensitive to the CPU, then I see that, okay, if he some overbooked in the CPU, then he will lose his performance. But memory, if you overbook, he will not lose that much performance. So how can we make this CPU, memory and disk balance between, when you are packing or when you are like putting them on the same physical machine?
Maybe ask a question like this. So if you have identified that you have this AIO stress which is not very sensitive to the CPU, you realize that you can reduce the CPU a bit.
Because then if there is overbooking happen, I can reduce, I will not lose too much performance because he is not that much sensitive.
Yeah, but then if you have done that reduction, so now you're running on 95% of your performance instead of 100% of performance as you reduce it. If you would continue to cut CPU further on that one.
So that's why I said that this is an acceptable level, and this is related to your SLA. So how much you are negotiating. If you say that no, I promise you, but as you said, there is no performance guarantee, but I will not cut down that. It depends on the level actually. So how much level you want. If I say that, okay, I need more than 90%, so I will never, never put IO stress with this. So, and I will not cut down for this Apache more so that it will lose more performance.
I think what I would like to understand is that, is this still, after you've done that reduction, is it still unsensitive to changes in CPU?
Yes, it's still more sensitive. You lose. How much you cut down, it will become more sensitive, and then it will lose the performance a lot. Yes.
But so even though it originally was not very sensitive to CPU, so if you have IO stress, where which is not sensitive to CPU.
Okay.
So then you can reduce CPU a bit.
Yes.
And not have a lot of you reduce performance a little bit. So now you sort of see that CPU has now become at least part of the bottleneck. If you then would continue to reduce CPU even more, would you still not see a large impact of that?
Obviously, there is a threshold. You cannot get it to the closer to the to the nil value, or you are starving too much. There is obviously a gap. So that's why we put like one graph where we have 3 different resource requirement. So if you make this, this is in the one of the graph, we have 3 different resource requirement for the same application, and we try to see that if I allocate a little bit more to him, how much he lose. If I allocate a little bit less to him, how much he lose. So obviously there is a threshold. You cannot go actually to the 0 that he lose all the performance.
So what I'm trying to understand is that if you really have found out what are the most sensitive resources, or if what you do is actually to identify what is a tight baseline.
So we try to find out for this, suppose for AIO stress, like how much he is sensitive to CPU memory. We have 3 different numbers. If you look at the table, we have 3 different numbers, and these numbers are, between 0 to 1. So it just identifies, okay, if it is close to 1, that means this means highly sensitive to CPU, but if it is close to 0, that means it doesn't care too much. You can reduce the performance. You can make some overbooking on that dimension for that. So we try to actually find, like, reveal the actual sensitivity, actual numbers. So this is not a binary 0 and 1. It's a number.
Yeah. The information is useful in any case, but I'm not totally convinced about what if this is if you identify what parameter is the true sensitive one for when you increase and decrease the amount of capacity, or if it's just that you identify what is a very tight baseline that you would do very well with.
I mean, this is the, I would say this is a not you can say it's a tight baseline. I mean, tight baseline on that sense it reveals, I mean, I guess, okay, sensitive to CPU is 1. So then I know that if I do even 1% overbooking, he has a chance to reduce the performance like 20%. So I never go for that. And then if I do in the memory maybe 10%, so maybe still I have this acceptable level of performance. So that is like this, I mean, what should I say? This is like the reveal of the true sensitivity values, so that I can pack or I can overbook as well. I mean, here all the results is due to overbooking. I mean, when there is a contention you share, and then how much you lose.
I think that, I mean, that can't be done now. But if someone were to try to convince me totally in this discussion, then what it would be good to see would be that when you have found this baseline and you start from that, then try to
reduce more. I understand your
actually see what happens,
Mhm.
to see if this is a less sensitive parameter or if it's just that you find the baseline. So that would be an interesting experiment, but you can't do that today.
Okay, but this is another paper. I mean, where we get the, but then, I mean, he did it. I mean, he tried to make it more contention, and he tried to see that how it reveals his behavior. But this paper is more about we have the sensitivity values and how can we pack them and don't increase the operational cost. So I referred that paper here actually.
So then, in the end, that could be just playing with words. It could be, to me, it could be that what you do is not really overbooking, but rather tight bin packing, which still solves the same important problem. But that's playing with words.
But why you're saying I'm not overbooking? Because when I said overbooking 200%, so I have CPU 2, I actually give 4, and then I make the VM to start for 4, so they are sharing. So then he is not getting as much CPU as he wants. So this is actually overbooking. So this is, obviously it's bin packing because I'm doing the bin packing, but in a different perspective, right? I mean, now my intention is to have some performance for the same operational cost. Obviously it's bin packing because I'm doing the consolidation problem.
It's also a bit of playing with words. I mean, also if it's overbooking or not depends on what is the right level. And any overbooking will be when you go
below my or above my, yes.
Okay, but you're clearly on top of what you do. And useful. I also had some questions about the I think we had already captured that part. I'm moving into paper 7 instead.
Paper 7,
so
okay.
Where we talked about it could be useful if you could also make use of if you could predict the workload variations, then you could make use of that. I don't think we should go much more into that part of it, but I also wanted to. You say at one place that your approach is not intended to optimize VM to PM allocations over time.
For this, I didn't get the question. So what do you mean by so I didn't do it over time, or?
That your approach is not intended to optimize VMs to PM over time. I'm not sure. Not sure what you meant by that. It's in section 5.
Really?
It might.
In section 5, okay, I can try to find that. What I meant by that.
It's here, page 192.
Okay. Like the modeling addition, where?
Here. 192.
Okay. Modeling assumption and simplification. Okay.
Finally, our model is temporarily oblivious. That is, it's not intended to optimize.
Aha, okay. Yeah, so the thing is that, what I meant by that, so the thing is that I run this optimization only once. I mean, if you compare to the paper 5 and this paper 7, so paper 5 is a dynamic, request comes, it runs the optimization, it try to allocate, again request comes, it try to allocate. When the release is over, I mean the request duration is over, I mean how long you ask for that, then it release the resources. But here it's not like that, it's not doing over time. So I have the allocation, and I have the expected demand on that moment of time, and I know the upper bound, how much it is getting up, and then I try to consolidate it once. So I'm not running over time for different different varying demands. So that I meant by that.
Yeah. But is there any reason why you could not also just use it like that? If you run this right now and then you want to run it again when workload have changed a little
No,
bit from now?
no, because the main argumentation of this robust optimization is that why we use that, because now we are not assuming the perfect knowledge, right?
Mm.
So we are not assuming the perfect knowledge. Better we are saying that it's uncertain, it can vary.
Yeah.
So when you say that it varies, so we assume that we don't need to over time. I mean, you can do also, like you can look at the next 10, I mean historical data. You can say that okay, next 2 hours my load will be go out till 50% for some applications. So then you can also do that.
Yeah.
But here we didn't do it. I mean, we only do it, okay, we look at that, okay, it the virtual machines like 40 or 50 or gamma, depend on the gamma. These virtual machines can go up, we pack it. So we are assuming that next 3 or 4 hours or maybe 1 day, I don't know. So it can be go maximum 50% or it can be goes maximum 80%. So we set them and then we say that consolidate it. So we know that then we are safe somehow for that. We have the feasible solution.
Mm. So if we then try to see again if this is the or how this would work in if the scenario wouldn't be exactly the one you have, since you have quite a strict. I mean, you're running your long time running services only, for example. If you so as we discussed initially, that many
Mhm.
data centers have a mixed workload that
Mhm.
you might run high priority service
Mhm.
VMs and
Mhm.
together with other workloads including non-critical tasks and critical tasks.
Mhm.
You can have things that could be shut down and restarted elsewhere. You can have low
Mhm.
priority virtual machines that can be starved
Mhm.
and leave some virtual machines having a lot of capacity, others being starved and having almost no capacity
Mhm.
at all, or just
Mhm.
shutting down. And you can have migrations where you don't actually